In this presentation, we'll walk through the analysis of a proposed reaction mechanism. Consider the following three-step mechanism for a reaction. The first elementary step of the reaction involves the breaking apart of a chlorine molecule to form two chlorine atoms. This is assumed to be a fast step. The second step of the reaction involves the reaction of a chlorine atom with a molecule of CHCl3 to form HCl and CCl3. This step is labeled as a slow step and therefore will be our rate-limiting step. The third step is the reaction of a chlorine atom with a molecule of CCl3 to form CCl4. This last step is labeled as fast. Let's try to answer the question, what is the overall reaction, what are the intermediates in the mechanism, and what is the predicted rate law? So the first question is, what is the overall reaction? To answer this question, we add up all the reactants and products in the elementary steps of the reaction mechanism, but cross out any species that appear equally on both sides of the arrow. So what we're going to do is add up everything in these two mechanisms, or in this three-step mechanism. We see, for example, that we have chlorine atoms appearing on both the product and reactant side of the various steps. We have two chlorine atoms that we can cross out on either side. Similarly, we see that CCl3 appears as a reactant and as a product. We can cross that out as well. So what we have left are the reactants and products in the overall reaction. We have chlorine gas reacts with CHCl3 gas to form HCl and carbon tetrafluoride gas. This is our overall reaction. What are the intermediates? Recall that intermediates are species that do not appear in the overall reaction, but do appear in one or more steps of the mechanism. Specifically, intermediates are formed in one step of a mechanism and then consumed in a later step. In this example, we have two intermediates. The chlorine atoms were produced in the first step and then consumed in the second and third steps. The CCl3 is another intermediate that was produced in the second step and consumed in the third. So our intermediates in this reaction are the Cl atoms and the CCl3. Now let's find the predicted rate law for this mechanism. To find the predicted rate law, you have to start with the rate-limiting step. That's going to be the slow step. In this reaction mechanism, the slow step is the second step of the mechanism, so our rate law will be based on this step. First, we want to write the rate law for the elementary step identified as the slow step, so that's for the second step. The rate law for this step is rate is equal to some constant, we'll call it K2, times the concentrations of the reactants that appear in that step. So we have chlorine and CHCl3. Again, this is coming from this step right here. However, the species Cl is an intermediate in the overall reaction and not a reactant or product. Since only reactants and products can appear in the rate law, we have to find a way to get rid of the intermediate in this expression. To do this, we'll use the fast equilibrium approximation. This approximation assumes that the first step in the mechanism actually reaches equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction. So using the fast equilibrium approximation, we'll set the forward rate of that step, K1 times Cl2, to be equal to this reverse rate, K minus 1 Cl squared. The square is coming from the coefficient 2 in front of the Cl. We can rearrange this expression to solve for the concentration of Cl. Here we have the concentration of Cl is equal to the square root of K1 times the concentration of Cl2 over K minus 1. We can then substitute this expression back into the above rate law, the one from step 2, and combining k's into one rate constant, we have rate is equal to K2. Here's our piece representing the Cl concentration, and here's our concentration of CHCl3. Rearranging this and putting all the constants together into a K prime, we get that the rate of this reaction should be equal to a rate constant times the concentration of Cl2 raised to the 1/2 power times the concentration of CHCl3. This is an example of a rate law that is first order in CHCl3, but actually half order in Cl2. Although we typically only consider 0, first, and second orders in this class, we see that more complicated mechanisms can lead to other concentration dependencies.